Okay. All right. So now for this one, how would you determine the ml quantum number? Okay, so in an atom, our electronic states are numbered by a few quantum numbers. So before we get to ml, there's n, which is our principal quantum number. And this guy goes from 1, 2, 3 up to infinity. And this basically numbers the states and is what defines our energy. So in a hydrogen atom, well, largely defines our energy, I would say. In a hydrogen atom, right, the energy is minus R over n squared, so that's the n. And so whatever state you're in, that's what the principal quantum number is. And so 1 is the lowest, and infinity is the highest. Okay, so L is our orbital momentum quantum number. And this can be roughly thought of as shape for our orbital. So L goes from 0 up to n minus 1. So again, it takes integer values, but it only goes up to n minus 1. So if n equals 0, L only equals 0. If n equals 1, then L can be 0 sorry, there we go, that threw me for a second. If n equals 1, L can only equal 0. If n equals 2, then L can only be 0 or 1. Now the L quantum number is typically relabeled as our SPDs, right? So if L equals 0, that's an S. If L equals 1, that's a P. If L equals 2, then that's a D. Or if L equals 3, then that's an F. Right? So that's the reason why there's only a 1s subshell. There's no 1p, so on and so forth. That's why there's only 2s and 2p, no 2d, no 2f. That's why you only get up to 3d, and that's the reason why you only get up to 4f here. If L increases further, then we would just call them, we would just follow alphabetical order. So L equals 4 is G, 5 is H, so on and so forth. But in our periodic table, we only get up to F shells, or we only observe electrons in F shells. Although with excitation, we can hit more exotic shells. Especially in molecules, I should say. Okay, so now we've got N and L. So then ML is our magnetic quantum number, or our azimuthal. And this is largely direction. So ML is minus L up to plus L. So it takes on every value from minus L to plus L. So in an S subshell, so L equals 0. So an S shell, ML equals 0, right? It can only have the value 0. So that's the reason why we only have one S shell, which can hold 2 electrons, as there's 2 spin quantum numbers that can differentiate them. And in an L equals 1 shell, so a P shell, ML equals -1, 0, or 1. That's the reason why we get 3 P shells, each being able to hold 2 electrons for a whole total of 6 electrons. And an L equals 2 shell or a D shell, we have ML equals -2, -1, 0, 1, 2. That's the reason we get 5, which can hold a total of 10. And in an F shell, we have ML -3, -2, -1, 0, 1, 2, 3. And that's why we get 7 total orbitals. So 3, 4, 5, 6, 7, which can each hold 2 for a total of 14 electrons. Okay, so those are our ML values, which are possible. How you would actually determine an ML value is actually not really possible, as the electrons are going to be inhabiting many of these in a superposition, and so they're not really that meaningful. They just define the orbitals which are possible. Okay, so then this kind of defines, along with the MS values, which I didn't talk about, but that's just the spin on the electrons. And okay, so I would say this is correct. So it defines the ML values, so solution is correct.